Hello my people, hope we're doing well. This is the third and the final video for review of parametric equations and their graphs. And I wanted to put a couple in there that were, atypical, just to sort of, help us to see this from all different perspectives and, play with it just a little bit. There really is nothing that helps conceptual understanding than playing around with a mathematical phenomenon from several different perspectives. And of course, I've basically climbed up on that soapbox before, so I won't do it again. But we'll just leave it at that, and we'll go ahead and get to this now. This actually winds up being the equation of a curve that I've mentioned before called the Witch of Agnesi, and it looks like this. Now that we've seen stuff like that before, but we're used to it being in this form when we're dealing with it in terms of rectangular or Cartesian equations. So let's eliminate the parameter and see if we can actually get it into something like this. Now, we know that cotangent of theta is going to be x over 2. Well, that basically means that I have, let's go ahead and construct the triangle so that we can figure out these values as we move along. And we know if this is theta, that cotangent is adjacent over opposite, and that the hypotenuse is going to be the square root of x squared plus 4. Now, theta is therefore the arc cotangent of x over 2. Now, if that's the case, and I don't have to plug in, but I will, we know that 2 sine squared is 2 sine of arc cotangent x over 2 quantity squared. But the thing is that it doesn't really matter putting this in here. As long as this ratio has helped you construct a triangle around theta, you can just take the sine of the theta, right? And so y is equal to 2. Well, sine is opposite over hypotenuse. So it's 2 over the square root of x plus 4 quantity squared. Now this 2 gets squared and becomes a 4, combines with that 2 and becomes an 8. And what I have is 8 over x squared plus 4. And that is indeed in this form. And if you look at this graph, that is exactly what this graph does, okay? If you plug in a 0 for x, you're going to get 8 over 2, or 0, 2. If you plug in a 2 for x, you're going to get 8 over 8, or 1, which is this point right here. If you plug in a negative 2, you're also going to get 1 because of the squaring. It's an even function, right? If you plug in 4, obviously you're going to, just on and on and on. You get the idea. But basically, just from a visual perspective, we can see how this certainly does generate this graph. Alrighty. Well, we've talked about going from parametric to rectangular. What if we're asked to go from rectangular to parametric? Because remember, we talked about in class how there's actually an infinite number of ways that you can do so. And sometimes you need to do it strategically and sometimes you don't. So notice that down here we need to do it strategically so that we get a particular ordered pair at time t is equal to 1. But let's just go ahead and think through as many different ways as we can of finding parametrics for this. Now, the easy way is just, if x is equal to t, then y is equal to 4 over t minus 1. And the way that you would eliminate the parameter is simply plugging in an x here for the t, since they're synonymous. Well, let's say that I want to do something different. Let's say that I need, let's say that I want y just to be 4 over t. Then t needs to be x minus 1. And if t is x minus 1, then x is t plus 1. Okay, well, what if I wanted to get rid of the denominator for my y, and I just wanted y to be 4t? Okay, well, now we need to do a little bit of work, okay, and we can't do it all in our head. If basically in order for t to become this, t needs to be equal to 1 over x minus 1, which means I get tx minus t is equal to 1, or tx is equal to t plus 1, or x is equal to t plus 1 over t. And if x is equal to t plus 1 over t, or you can, separate the fraction and do it like that, x is equal to t plus 1 over t, then of course you would work backwards to get t is equal to 1 over x minus 1, and when you plugged it in for t, you would get 4 over x minus 1. And so basically you can do this just in a number of different ways. You simply have to kind of work backwards, decide what you want for one of the equations, and then work backwards from the eliminating the parameter aspect to get the other. And I think 3 is fine. We were only, in this case, asked for 2. All right, let's go ahead and look at this one. It says, find a set of parametric equations for the rectangular equation that satisfies the given condition. Okay, well, let's go ahead and let's forget this right here for a second, and let's just do the easiest one to turn it into parametrics. I know that if x is equal to t, and y is equal to 4 minus t squared, right? Oh my gosh, will you look at that? Because if I just do the simplest one, it does give me 1, 3 at t is equal to 1. Because you plug in 1 for t and you get 1, you plug in 1 for t and you get 4 minus 1, or 3. Okay, well that was a little bit too easy, right? So at t is equal to 1, you get x of 1 is equal to 1, and you get y of 1 is equal to 4 minus 1 squared, or 3. And of course that gives you the order pair 1, 3. Check. But that's a little too easy. Let's say that we wanted something like t is equal to 1 at the point, and of course all we got to do is just pick another point that we know of on this curve right here, and we happen to know that 2, 0 is on that curve. Okay, well, let's go ahead and take a look. Let's say that if t is equal to 1, I need an output for x of 2. Can I just say 2t? Sure, I can do that. Well, if x is equal to 2t, then you can just plug 2t in for x right here, and y becomes 4 minus 4x squared. And at t is equal to 1, I get 2 and 0. Okay, well, there's another way to get that. Could I have said t plus 1? Because if I plug in 1 into here, I get 1 plus 1, and that's another way of getting 2, obviously. Would it be the same? Could I go ahead and say y is equal to 4 minus t plus 1 squared, and would that be, okay, well, let's go ahead and plug in t is equal to 1 into that. I'm going to get 4 minus 2 squared. Yeah, and I could simplify it, but I don't have to. And I could do 4 minus t plus 1 squared, and I get basically an alternative way of arriving at 2, 0 at t is equal to 1. And I could probably do it in a whole host of different ways. I could do another way to get 1 for x would be x is equal to 2t minus 1. And then I would just have to plug the 2t minus 1 in for the x. And then, of course, that one you may want to simplify. But you don't have to. So, 4 minus 2t minus 1 squared. And, if you plug in t is equal to 1, you're going to get 2 minus 2 minus 1, that's going to be, oh, sorry, I'm looking for 2. Sorry, I was still thinking about the 1, 3. So this actually would be another way to do the 1, 3. That would be up here. But, I mean, basically, my whole point is that you can do it in a multiplicity of ways. You just, whatever you designate for x that's going to give you your sought-after x output, you then plug that in for the x expression right here, and then y becomes 4 minus whatever that is squared. And, of course, we can sort of extrapolate that out to other equations that we're being asked to find the parametrics for. And let's do a couple more examples. Parameterize, yeah, that's one of those words that I just gets caught in my mouth and gets garbled, and I either wind up with too few or too many syllables as it comes out of my mouth. So I'm gonna prefer to And I'm going to prefer to talk about it like this, okay? Write parametric equations 4. It's more syllables, it's more work, but I don't sound like I have marbles in my mouth when I do. So, okay, if I have y of x is equal to 3x squared plus 3, well, there are plenty of ways that we can do this. If x is equal to t, then y, of course, is going to be what? Well, then it's just 3t squared plus 3. Okay. Well, let's go ahead and do it another way. Could x be equal to t squared? Sure, so long as y is equal to 3t to the 4th plus 3. Could x be equal to e to the t? Sure. You just have to make sure that y is equal to 3e to the 2t plus 3. Now, these are, of course, different because this one is basically going to wind up being the same domain, the same shape as this. The problem with this one is that you're never going to get negative x values. And this one, x is not just non-negative, it's positive all the time. So these are a little bit problematic because of the way that they change the graph by literally chopping part of it off. But as long as the domain or the interval that you're really interested in is still a part of the graph after imposing this and chopping pieces off, then you're just fine. Okay. It all has to do with, do you still get a portion of the graph that is meaningful for you? But you do need to be aware that these two do wind up chopping pieces off. And let's go ahead and look at that. Let's go ahead and boom. Okay, so we'll do t and then 3t squared plus 3. And then we'll do t squared and then 3t to the 4th plus 3. And let's go ahead and let's go ahead and limit the window a little bit. Let's go, t negative 10 to 10. X, I know that this is going to be stretched and it's going to be wholly above the axis. So, and I know it's going to be narrow. So let's go negative 5 to 5 instead. And let's go 0 to 10. And this is our graph. Notice what happened. I don't know if you could tell, but basically half of the graph is blue because when it graphed x1, y1, it graphed the whole thing as blue, and then came in just a little bit later and wrote over the right-hand side of the graph in red to designate the x2, y2. Notice x2, y2 is red. And what we're going to do is let's go ahead and let's do e to the t, and then 3e to the 2t plus 3, right? And this should look like the same thing. We should see the blue graph, and then the red graph should cover up the right-hand side. And the only difference between this and this is that this will include x is equal to 0, and this one will not. See, blue, and then red on the right-hand side. Okay, let's go ahead and let's do this last problem right here on this page. I noticed that, if it helps, this winds up being something like that, okay? Now that could help, that could not. The easiest thing to do, and notice that this is x in terms of y and not y in terms of x. You're probably going to have to reverse the whole thing. So you have x in terms of root t plus 2t, and then y in terms of just t. And this would allow you to take the y and to substitute it in here. Well, if you wanted instead for y to be root t, then, you could do x is equal to t plus 2t squared. Couldn't you? And that's actually not the case. What needs to happen here is it needs to be t squared. because if it's t squared, then t is root t in here, and over here at the t squared, the y gets plugged in by itself. And of course, you would have to then talk about the fact that here, this right here designates the fact that t cannot be negative. And that's fine because, you know, you have a restriction here as well. But again, it has everything to do with what interval are you really hoping for your parametric equations to exist over, and what portion of the graph are you interested in. Okay, last question. And this is just, and this should be relatively easy. Explain the difference between the graphs of the two pairs of parametric equations given below. Well, you should notice that both of those are hyperbolas. I mean, the first one obviously is. It's 3 plus 4 secant and 2 minus 3 tangent. We've dealt with something like that before. The thing is that this is also a hyperbola, because remember that when we transform sine squared x plus cosine squared x is equal to 1 into cosecant and cotangent, we divide by sine squared, and it's 1 plus cotangent squared is equal to cosecant squared, and therefore cosecant squared minus cotangent squared is equal to 1. So this has a certain parallel to the secant squared, right? The one that we use over here for this one over here is secant squared x minus tangent squared x is equal to 1. So if this is the case over here, and this one becomes the secant right here is x minus 3 over 4, so x minus 3 over 4, and the tangent is y minus 2 over negative 3. Here, the cosecant is exactly the same as the secant expression over there on the left, and it's x minus 3 over 4, and of course y minus 2 over negative 3 for the cotangent. And these, of course, are going to be equivalent. They're going to give us exactly the same graph and exactly the same equation in rectangular Cartesian form. The difference, of course, is exactly the same thing as when we took that ellipse and we swapped sine and cosine. It's a matter of direction, and it's a matter of when is the graph, meaning at what value of t is the graph at a particular point. So location and directionality at a particular t value will be the difference between them. Well, I hope this sort of smattering of parametric equations and their graphs and has been helpful in sort of bringing back to your remembrance conceptual understanding and familiarity with parametric equations and their graphs. And of course, we'll iron out any further questions that you have tomorrow before we jump into applying calculus to those things. As always, if you have a question, shoot me an email. Bye.